Swayam Prabha. Digital India. Educated India.
Good morning. So, நேற்றைக்கு லெக்சருக்கு அப்புறம் கொஞ்சம் எல்லாரும் என்ன பண்ணீங்க? Did you go and study something? கொஞ்சம் பார்த்தீங்களா எல்லா லெக்சரையும் மெட்டீரியல் தான். நேற்றுக்கு மிஸ்ரா வந்து பேசினாரு. அப்புறம் இன்னொரு ஃபேக்கல்ட்டி பேர் ஞாபகம் இல்லை. அவர் யாரும் வந்துட்டா அன்பர்சனா வந்துட்டாரா? அவரே லெக்சர் எடுத்தாரா? ஸோ நேற்றுக்கு 3 லெக்சர் இருந்ததா? 3 செஷன் இருந்ததா? ஓகே. ஸோ என்ன கேட்குறது எனக்கு நீ பேசுறது சொல்லு. சரி, இப்போ NMR ஸ்பெக்ட்ராஸ்கோபி சங்கர் ராமன் ஏதாவது பேசினா இல்லை? அவர் ஸ்டீரியோ கெமிஸ்ட்ரி எடுத்தாரா? ஃபர்ஸ்ட் லெக்சர் ஸ்டீரியோ கெமிஸ்ட்ரி NMR எடுக்கல இல்லையா? யாராவது எடுத்தாங்களா இது வரைக்கும் NMR ஸ்பெக்ட்ராஸ்கோபி? யாரும் எடுக்கலையா? நீங்க என்ன படிச்சிருக்கீங்க? யார் எடுத்திருக்கா? சங்கராமன் NMR எடுத்தார் இல்லையா? கொஞ்சம் என்ன சொல்லி கொடுத்தாரு ஸ்பெக்ட்ராஸ்கோபியில? சத்தமா சொல்லு, எனக்கு எக்கோ வருது. டைனமிக் ப்ராசஸஸ் NMR சொல்லி கொடுத்தாரா? அப்போ அவர் ஏதாவது தியரி இதையும் சொன்னாரா? பேசிக் தியரி, ஸ்பின் தியரி ஏதாவது சொல்லி டீச் ஒன்றும் சொல்லு. சரி. ஸோ வாட் ஐ வில் டூ is to give you again a fairly rigorous but basic treatment for nuclear magnetic resonance spin. Nuclear magnetic resonance spectroscopy is probably the most important spectroscopy for chemists, physicists, and biologists. And of course, today, medicine uses NMR through the magnetic resonance imaging, MRI. MRI is useful for finding a lot about the body, particularly about cancer, and locating very specific issues of cancer in various parts of the body. Also, MRI is useful for finding other the physiological defects in the system through what we call as a non-destructive technique. Because what you do is in MRI, you slide into a magnetic field and all your magnets, water magnets, proton magnets, sort of get magnetized, and then they have the processes to follow. And then when you come out of that magnet, your proton becomes normal. Okay. So it's not like the X-ray. When you shine X-ray on your body, X-ray kills some cells, tissues. So X-ray is a destructive technique to determine the bones and the skeletons. But X-ray also has difficulty that tissues cannot be carefully examined. You want to examine tissues and you want to examine parts of the body that X-ray cannot probe. NMR seems to be very useful. Magnetic resonance imaging is a famous technique. So today, not only for medicine, also for understanding the structure of proteins and protein enzyme interactions and the biological processes and industrial processes. Today, MRI is also used, magnetic resonance imaging is used in material science in the industry. So, NMR has become an extremely important technique for everybody. All of this is possible because nuclei in atoms and molecules, nuclei have a fundamental property called the spin quantum number. Okay? Not all of them have the spin quantum number. Nuclei which have even number of protons and even number of neutrons do not have a spin quantum number. Okay? Carbon-12, a very famous example. Carbon is so important in spectroscopy, in organic chemistry, and in chemistry as a whole, but carbon-12 cannot be detected by NMR. Oxygen-16 cannot be detected by NMR. Likewise, nuclei which have even number, even protons and neutrons do not have a spin quantum number. All the other nuclei have a spin quantum number. But fortunately for us, carbon also has an isotope, C13, which has 6 protons and 7 neutrons. So it's an even odd combination. And carbon-13 is spin 1/2. Except that it's a very small fraction in the natural abundance. I think it is some 0.7% or something like that, carbon-13. So if you want to do carbon-13 spectroscopy, you must enrich the sample with carbon-13. Proton, on the other hand, is not a problem. Proton also has a very strong magnetic moment, nuclear magnetic moment, because it has a property called the gamma gyromagnetic ratio, which is very large. So proton is one of the best things for study in NMR. Proton is also a spin-half system, and therefore everything that we know about electron spin earlier is also applicable to proton spin. Just to give you a brief introduction, magnetic resonance was first proposed and experimentally seen in a different context by a physicist in the 1930s. But the resonance that we see today, that we do experiments today, the first experiment, successful experiment, was done in 1946 by 2 groups of people. Felix Bloch in Stanford University in the USA is one group. He had 2 of his assistants, associates, and Edward Purcell, who was in Harvard University in the side on the eastern side of the continent. Stanford is on the western side of the continent. Edward Purcell was the other researcher. Both of them were successful in getting the first NMR signals by different means. And they both won the Nobel Prize for Physics in 1952 for their contribution to understanding magnetic resonance. But that was a physics phenomenon. The chemistry of NMR came around 1949 or 50 or 51, around that period, when the nuclear magnetic resonance spectrum of ethanol was measured. And then, surprisingly, ethanol gave 3 signals. The understanding of those 3 signals immediately gave a complete door open. It made a complete door open for understanding chemical structures. And NMR has now taken over from physics by many chemists to do structural and also property studies. Okay? Now, this is because of the spin nuclear magnetic moment. So let me open up the first file. Okay? The important thing is spin itself was a proposal and quantization of the spins. That is, spins have discrete values. They don't have continuous values. This was illustrated by the famous experiment in 1927 by Otto Stern and Gerlach. I will not have the time to explain it, but maybe we will see a little bit of that. To understand the magnetic resonance from the quantum mechanics point of view, one must study the properties of angular momentum. And one must see what happens to the nuclear spins or molecules or atoms which are placed in static magnetic fields and also time varying magnetic fields. This is the static magnetic field is called the Zeeman magnetic field. And the interaction of the nuclear spin in the Zeeman magnetic field is given by a term called the Zeeman Hamiltonian. The presence of this gives rise to energy levels for the nuclear spin. And energy levels are separate. And the gap between these energy levels for a spin 1/2 depends on the magnetic field. So we will see some of these things formally. Okay? The first thing that you need to understand is the nuclear spin angular momentum. Angular momentum is a vector. You remember physics, you recall that angular momentum is given as r cross v, where r is the distance about the axis and v is the momentum for the particle going along the axis. That's a classical picture. Spin does not have a classical analog. Spin is known as an intrinsic property of the nucleus, which has odd number of protons and even number of neutrons, or odd number of protons and odd number of neutrons, or even number of neutrons and odd number of neutrons. Odd is fine, odd even is fine, even odd is fine, even does not contribute. The angular momentum, spin angular momentum, is given by the dimension h bar h by 2 pi. H is Planck's constant. So if you write this as a dimensionless angular momentum, h bar times I does not have dimension, everything is here. So the angular momentum is given in terms of I, and the Stern-Gerlach experiment suggests that the angular momentum and nuclear spin magnetic moments are quantized, meaning discrete values. They cannot take all the values between some range. They take only specific values. And a spin 1/2 system, what is the experiment? The experiment is to send a beam of spin 1/2 systems, okay, magnetic ball. Here, in the presence of the magnetic field is between the two poles of the magnet. But you see that this pole is triangular. This pole is vertical. So what it means is that the field here in this region is different from the field here in this region, and is different from the field here. So there is an inhomogeneous magnetic field that is created by this kind of magnets. If you put a rectangular bar here, then the field is homogeneous. So nothing happens. You need an inhomogeneous magnetic field, and in that field, the bunch of nuclear spins centrocephaly split into two beams, okay? And only two beams. This is for the electrons. If you send some other nuclei, you may get 3 beams. Some other spin, you may get 5 beams. But the point is the finite number of beams and nothing in between. And it is immediately calculated that the z component of the magnetic moment is due to a spin angular momentum I, and the I has a value +1/2 or a -1/2. That can be calculated using simple magnetic formats. Okay? So spins, therefore, in a magnetic field split into 2 possible configurations, a spin up configuration and a spin down configuration. So these are the two energy levels. Now, we'll see more about that in some other lecture if we have time. And there is a, yeah, go ahead. Oh, I didn't share the screen, right? Oh boy. I didn't share the screen so far. Aha. Yeah, now I'm sharing the screen. Sorry. Can you see that now? Just one moment. Yeah, I'm sorry. Is everything okay now? Yes? Can you see the screen? Hello. ஏன் முதல்ல சொல்லல கேமரா ரோல் பண்ணு இப்பதான் ஆரம்பிக்க போறோம் ஓகே ஸோ சினிமாவில் எல்லாரும் பார்த்துருக்கீங்களா டேக் 2 பார்த்துருக்கீங்களா ஓகே ஸோ இப்போ ரீல் 2 டேக் 2 நோ we'll start all over again. Okay. Yeah. எவ்வளோ இது இந்த படம் வந்துருச்சா தக் லைஃப் படம் வந்துருச்சா தியேட்டரில் வந்துருச்சா தியேட்டரில் வந்துருச்சா எவ்வளோ பேர் பார்த்தீங்க யாருமே பார்க்கலையா பட் படம் வந்துருச்சு சரி நான் இன்னைக்கு ரொம்ப ஆக்டிவாக இருக்கிற முக்கியமான ஐட்டம் வந்து அது எல்லாருக்கும் அந்த படத்தை பார்க்கணும் அந்த படத்தில் நிறைய பேர் சொல்கிறாங்க நல்லா இருக்கு நல்லா இல்லை சொல்கிறாங்க ஸோ போய் பார்த்தா தான் தெரியும் ஸோ அந்த மாதிரி படம் எடுக்கிறதுக்கு எத்தனை ஷாட் எடுப்பாங்க தெரியுமா ஒரே ஷாட்டை திருப்பி நம்ம இங்கே இதை வந்து ஒரே ஒரு தடவை திருப்பி எடுக்க போகிறோம் ஓகே த லெக்சர் ஸ்டார்ட்ஸ் ஃப்ரம் நவ் ஓகே ப்ளீஸ் ஓகே யா ஸோ we'll start with the elementary magnetic resonance. The first thing we'll study is the Stern-Gerlach experiment. Just very elementary. I wouldn't study. I'll tell you what it is. And then we will look at the nuclear spin angular momentum vector. Okay? So this is what I was telling. Angular momentum vector J has the dimension of Planck's constant, h by 2 pi, h bar. And I is the dimension-free, dimension without dimension, the angular momentum vector itself. The Stern-Gerlach experiment by Otto Stern and Walter Gerlach in 1927, it was a famous experiment. They first did the experiment around 1922, but the results were published a little later and understood by the two. And this experiment suggests that angular momentum of a nuclear spin magnetic moment, angular momentum, they are quantized, meaning they take only specific values. So the experiment that I was trying to explain to you was a spin 1/2 system. That is, a silver beam was sent, but it's essentially it's the electron, which was later that we look at it, we'll see a beam of electrons, suppose they are sent like this, through a magnetic field. If you look at the magnetic field, you see that this is a triangular field. Okay? You see this pole. This is the one pole is the south pole, the other is the north pole. Because of this shape, the magnetic field in this space is different from the magnetic field here, different from the magnetic field here, and different from the other. So it's not homogeneous, but it is inhomogeneous magnetic field. If you send a spin, an electron beam through this, you see that the beam splits into two beams. Now, if you take this beam and send it further by another exactly same pair parallel to this direction, magnetic field, this beam doesn't do anything. It just goes through. But if you take this beam and you change the direction of this magnetic field to some other direction and pass this beam through that, then that again splits into two beams. Okay? So the analysis is that magnetic moments and spin angular momentum are quantized, have only specific values. And in this case, this beam corresponds to a spin magnetic moment with a plus a half angular momentum, h bar. And this beam corresponds to the spin angular momentum minus a half h bar and the magnetic moment accordingly. Okay? Now, some other experiment we'll see Stern-Gerlach, some other lecture we'll see that. That is a very beautiful video and a very nice account of the history by one of our former professors, very famous physicist, physical chemist, Professor Chandra Kumar. He was also emeritus professor in our department, and he has given a video. You might be able to look for it, and if you need, I will send you the link. And also there is a very beautiful readable summary of the Stern-Gerlach experiment by Professor David Harrison from the University of Toronto, and there is a link where you can look for that. This file I will send to everyone so that you'll be able to copy this link and check. Now, the spin magnetic moment of any nucleus is connected to the spin angular momentum by this nuclear property called gyromagnetic ratio. The gyromagnetic ratio has the units of radians. Tesla is the magnetic field. 10,000 Gauss is 1 Tesla. So radians per Tesla per second. That's the dimension of gamma. And angular momentum is given in terms of h bar times Iz. So the precise measurement of gamma is possible experimentally, and there are methods available in physics experiment. And the values of gamma are also tabulated for all the nuclei that are known to have a spin quantum number. So, for example, proton has a gamma value of 26.7522 multiplied by 10 raised to 7. So gamma divided by 10 raised to 7 is this much. So gamma is 26.7522 times 10 raised to 7 radians per Tesla per second. Okay? If you take carbon-13, which is an even odd nuclei, even protons and odd number of neutrons, has a spin a half. Its gamma value is 6.72, roughly 1/4 of that. Okay? This is 4 times the carbon-13 value. Nitrogen-14 is a spin 1. Deuterium is a spin 1. And 17 oxygen is a spin 5/2. 27 aluminum is a spin 5/2, and so on. And chlorine-35, very well known, very important nucleus is spin 3/2. And 19, fluorine-19 is also spin 1/2. Okay. Fluorine-19 has a very strong gamma value, similar to that of the proton. You see, this is 26.7, this is 25.1815. Okay. Quite close, very strong nucleus. So fluorine NMR, proton NMR, carbon NMR, and phosphorus NMR. I have not given the value for phosphorus NMR. All those things are quite well known. Okay. Now, gamma, if you see the dimension, gamma is radians per Tesla per second. So if you multiply gamma by Tesla, magnetic field, this will cancel out with the Tesla. So you will have radians per second. Radians per second is angular frequency. Okay. Therefore, Gamma multiplied by the field, magnetic field H naught, is typically angular frequency. And the radio frequency range is where these things happen. Therefore, the radio frequency range is 10 megahertz to a gigahertz, that is 1000 megahertz. That's the maximum field that we have today. It's a fairly strong field. So gamma H naught is the angular frequency, and gamma H naught multiplied by 2 pi per radian gives you the linear frequency, because omega is 2 pi nu. Okay, so omega divided by 2 pi, 2 pi radians gives you the linear frequency nu. Okay. Sorry, I got this wrong. This should be 2 pi down here, and radian should be up there. So, okay, so 2 pi radians. This should be gamma H naught divided by 2 pi. Sorry, that should be nu. Okay. Now, you can calculate for a 100 megahertz proton spin NMR spectroscopy, NMR spectrometer, has a resonance absorption frequency of 100. When you say 100 megahertz, the resonance absorption frequency for proton is 100 into 10 raised to 6 hertz per second is hertz. That's what is the meaning of these spectrometers. When you say 200 megahertz spectrometer, 500 megahertz spectrometer, they all refer to proton resonance absorption frequency. Okay. Now, let's do a small calculation, as we always should do, to understand these things. The magnetic moment, the Z component of the magnetic moment is the Z component of the angular momentum. H bar I is the angular momentum multiplied by gamma. So mu Z is gamma H bar times Iz. Now, Iz can only have plus or minus a half from the Stern-Gerlach experiment. Therefore, the value of mu Z is gamma H bar by 2 or minus gamma H bar by 2 because of plus and minus. Okay. Also, quantum mechanics tells us that the angular momentum operator J, the magnitude of the angular momentum operator J is H bar times square root of I into I plus 1. You would have seen this in your electron magnetic moment or the crystal field theory and ligand field theory and so on. If you have not seen this before, you have seen there. So I into I plus 1 is the magnitude of J multiplied by H bar. Therefore, for a spin 1/2, the magnitude of J is 1/2 into 1/2 plus 1, which will be 1/2 into 3/2 square root. So it is H bar root 3 by 2. The value of Jz or either plus H bar by 2 or minus H bar by 2. So you can see that if a vector has a magnitude which is greater than its components, then the vector and the components are not in the same direction. Okay? You can see that here. Okay? Suppose this is the direction of the magnetic field, Z, H, in this direction. You can see that the spin 1/2 has a magnitude of root 3 by 2, but it has a Z component. This is the projection of this here. This Z component is only 1 by 2. So if this is 1 by 2, this is root 3 by 2, there is an angle. What is that angle? Cos theta is 1 by 2 divided by root 3 by 2. So you can see that cos theta is 1 by root 3. This angle is called the magic angle. The value of theta is 54 degrees 7 minutes. Okay. So what it means is that the spin angular momentum in the magnetic field is not along the magnetic field, but aligned at an angle 54 degrees, or aligned at an angle. If the whole thing is 180 degrees, this angle is, this is also theta, so this angle is 180 minus theta. So 54.7 or 180 minus 54.7. This is minus a half, this is plus a half. Okay. So cos theta is 1 by root 3 plus or minus, and so you can see that theta is either 54.7 or 125 degrees and 3 minutes. So the spin angular momentum is aligned like this. It's not static. It actually undergoes precessional motion. The spin angular momentum precesses about the magnetic field H, such that its x and y component in this plane get averaged to 0. Okay. The z component always remains as a half or a minus a half. If the spin is aligned like this, it precesses like this. Okay. It's called the precessional motion. Now, when a magnetic moment is in an external magnetic field, H naught Z, that is this field, the Z direction. H naught is the magnitude of the field. 1 Tesla, 1.5 Tesla, maybe 3 Tesla, or maybe 5 Tesla, something like that. Okay? That's a field. So in that field, along, called the z-axis, the interaction energy of the magnetic moment is minus the magnetic moment vector scalar product with the magnetic field H. This is the interaction energy. And since H is in the z direction, this will only get the z component of the magnetic moment. So this is minus mu z H naught. But you know mu is given by gamma, H bar, and I. So the Zeeman interaction, this is the Zeeman field. The Zeeman interaction Hamiltonian is minus, you substitute for mu as gamma, H bar, Iz times H naught. So if you take the H bar out and you put gamma H naught, you see it's minus H bar omega naught Iz. This is the Hamiltonian. Please remember, in quantum mechanics, angular momentum is an operator. Therefore, the z component of the angular momentum is also an operator. It has two eigenvalues, which are the plus and the minus a half. Okay. Which are the plus and the minus a half. Those are called the eigenvalues of Iz. So spin 1/2, when you put in a magnetic field, it has a minus H bar omega naught. See, omega naught contains the magnetic field. So if you put the magnetic field stronger, the interaction is stronger. If you put a weaker field, the interaction is weaker. The spin 1/2 has two energy levels because Iz is either plus a half or minus a half value. So you can see the lower energy is minus H bar omega naught by 2. The upper energy is with a minus 1/2, this minus, it becomes plus H bar omega naught by 2. So you can see the picture that the lower energy for a spin in a magnetic field H naught is minus H bar omega naught by 2, and the upper energy is H bar omega naught by 2. The difference between the two is H bar omega naught. This is important because in NMR, you cannot do resonance spectroscopy without an external magnetic field. You need to put the external magnetic field to create the energy level differences between the two nuclei. Okay? That's the most important part. Okay. Two nuclei, if you increase the field, the energy level keeps increasing. Because it's proportional to omega naught. Omega naught is H naught, gamma H naught. Therefore, if you have a small field, the energies are close. If you have a strong field, the energies are more. If you have a very strong field, the energies are very different. So the energy difference is proportional to the strength of the field. So a 100 megahertz NMR spectrometer corresponds to the gap between the two frequency as 100 megahertz for hydrogen, for proton. A 500 megahertz NMR spectrometer is 500, very far. So the energy levels are well separated when you use a spectrometer of higher resolution, higher magnetic field. And these are important because the nuclear energy levels are already very small energies. They are in radio wave frequency, 100 megahertz, 200 megahertz. That's a frequency. If you calculate the energy, remember, you can do a simple calculation. Please write down what I tell you. H is, please write down. H is 6.627 times 10 raised to minus 34 joule second. H by 2 pi, you write as H by 6.28, 3.14, 2 pi is 6.18. So that's H bar. Okay. Now, times, what is this? 6.627 into 10 raised to minus 34 divided by 6.28, right? That is H bar. Now, suppose omega naught is 2 pi times nu naught. And let us assume nu naught is 100 megahertz. So 2 pi times 100 is omega naught. Okay, write that down. So H bar is H by 2 pi. Omega naught is 2 pi nu naught. So what is H bar omega naught? Product. 2 pi's will cancel. 6.627 into 10 raised to minus 34 joule second. And when I said 100 megahertz, it is 100 into 10 raised to 6 per second, right? A hertz is a per second. So it is 10 raised to 8. What is the value? H bar omega naught. 6.627 times 10 to the minus 26 joules, right? Minus 34, and you have 10 raised to 8. So 34 and 8 will cancel to give you minus 26. So H bar omega naught is energy 6.626 times 10 to the 26, 10 to the minus 26 joules. That's the energy per one spin. So multiply by the Avogadro number of spins. 1 mole. 1 mole of proton. How much will you get? That is 6.022 into 10 raised to 23. Avogadro number is 6.022 into 10 raised to 23. So forget about the 6 and 6, that's about 36. You have 10 to the minus 26, and you have 10 to the 23. So what's the product? 10 to the minus 3 joules, right? 36 into 10 to the minus 3 joules. Is it very large or very small for a mole of atoms? Extremely small. Extremely small. Therefore, the energy levels are very close to each other. Therefore, what happens is spins in the lower energy and spins in the higher energy, the numbers are approximately the same because they are so close to each other. The difference is If there are million spins in the higher energy, there are a million plus one spin in the lower energy. That's the only difference. That is the difference between the number is 1 in a million. Okay? So if you try to resonate, excite the transition from lower spin to higher spin, you don't get a good signal. It's 1 spin in a million. So the signal that you get, the magnetic signal that you get, is very, very weak. So NMR signals are fundamentally, inherently weak signals. You need to do careful experiments to find out a measurable signal. NMR experiments failed several times in the 1930 to 1945 period, 100 years ago. Several people tried to do magnetic resonance excitation. They failed. It was by very careful and judicious choice that Felix Bloch and Edward Purcell chose protons in water molecules to study the magnetic resonance, and they got a very weak signal in the oscilloscope. Okay? That's a very beautiful story. The story is Bloch was trying to measure this signal for many days. His associate, Hansen and Packard, there were 2 other people. His associate was checking the oscilloscopes every day, changing the magnetic field in the resonance measurement. They didn't get a signal. So Felix Bloch said maybe the experiment will not work. The story is something like a Friday. So Bloch said, okay, let's shut down the magnetic field. We'll all go to a shop outside, have something to drink. Okay? So in the US, it's a custom to have a happy hour drink, a beer or 2 in the evening. So they wanted to have a drink or something like that. So Hansen and Packard, they shut down the magnet. See, when you shut down the magnetic field doesn't go to 0 immediately. The magnetic field slowly goes down and then reaches 0. So it takes some finite amount of time. During that time, Hansen saw a flip in the oscilloscope and then disappeared. Okay? Small electric signal was seen in the oscilloscope and then it died. So curious he was, he said, okay, let me turn on the magnetic field from 0. So he turned on the magnetic field. And again, as the magnetic field was raising to the preset value that they had set earlier, the signal appeared in the oscilloscope and then again disappeared. Okay? So he was quite certain that there was something wrong with their calculation. So he did this experiment 3-4 times on the same day, and then told his professor, Felix Bloch, see, that this is what is happening. If I turn off the magnetic field, the signal comes and then goes. If I turn on the magnetic field, the signal comes and goes. Then Felix Bloch said, no, I understand. Maybe I did some calculations wrong and put the wrong magnetic field layer up. Maybe I should do the calculation again and put the field in the correct for signals to appear. They corrected it when they came back to the next field, and they got a beautiful signal. This is there in the Google. This is there in the internet. A beautiful oscilloscope signal for magnetic resonance in 1946. You can look for that and you can see an image of the oscilloscope. What is important is the signal is very, very weak because the magnetic energy levels are extremely close to each other. See, if you put an electron instead of proton, the electron's gamma value here for the electron is about 1800 times more than that of the proton because of the mass. Electron is 1800 times less lighter than proton, and gamma depends on 1 by the mass. Therefore, the gamma for the electron is this multiplied by approximately 1800. So if gamma is very large, you see that the normal frequency that we got, okay? Normal frequency is gamma H naught, gamma times the magnetic field. If gamma is extremely large, if you put the same field that you do in NMR, you see that the energy levels become so big, so different. The energy level becomes so different that there is a huge gap between the lower energy and the higher energy. Therefore, there are more electron spins here, less electron spins here. So it's possible for you to do signal enhancement by signal measurement reasonably well and promoting resonance. So the electron spin resonance signals are stronger than the proton spin resonance signals. That helps us to understand the magnetic resonance of electron spins or the nuclear spins better. Okay, so that's about the history. Now, again, when you study chemistry in the MSc, quantum mechanics will always keep coming to you. Okay, let's look at what it means. I told you that the plus a half and minus a half are eigenvalues of the IZ operator, Z component of the angular momentum. Okay, let's see that here. The spin up state is given by the symbol alpha, and this is the Ket notation that people use, and it was introduced by Dirac in quantum mechanics early. And alpha is given two numbers, 1/2 and 1/2. What are these 1/2 and 1/2? Please remember, alpha is an eigenstate. When you put the spin in a magnetic field, you have this lower energy state and you have the higher energy state. Alpha is this state, and it has the value 1/2 and 1/2. What are those 1/2 and 1/2? The operator is the square of the angular momentum. Please remember, it's I into I plus 1 is the eigenvalue. So I square has an eigenvalue of I into I plus 1 for the state alpha, and I into I plus 1 is 1/2 into 1/2 plus 1. The square root of this is √3/2, but the square of this is 3/4. Okay? So you see I square acting on alpha gives you 3/4 times alpha. So this half, which is the spin quantum number I, is this number, the first one. IZ gives you on alpha a plus a half. This is the lower energy state. This plus a half is this number. So the two numbers are eigenfunctions, eigenvalues of I square operator, eigenvalues of the IZ operator. What is beta? Beta is the higher energy state. The only difference is, please remember, I square has the same quantum value, number, eigenvalue, 1/2 into 1/2 plus 1, 3/4 for the beta. But IZ for beta has a minus a half. So you have 1/2 and a minus 1/2. This state is called the beta state. This is the spin 1/2 up and down states, or aligned with the field, aligned against the field, alpha and beta. Okay. So E lower has an energy minus h bar omega by 2, omega naught. E upper is h bar omega naught by 2. So the Hamiltonian is minus h bar omega naught times IZ. Hamiltonian has two eigenvalues, this one and this one, because the eigenvalue of Iz is plus or minus a half. So eigenvectors are alpha. So the state is called the alpha state, that state is called the beta state. So what is the Schrodinger equation? The Schrodinger equation is H on psi giving you E on psi has two solutions for a spin system. Spin 1. When you do a Stern-Gerlach experiment for, you have nucleus which has a spin quantum number 1. You see 3 signals coming up. The beam does not split. The beam also splits, and so there are 3 beams coming up. And one calculates the eigenvalues of the Iz operator as 1, 0, and minus 1. Okay? So I is 1. The square of I has a quantum number 1 into 1 plus 1, 2. But the Z component of the Iz operator has 3 eigenvalues, 1, 0, and minus 1. So these are the 3 states of a spin 1 system. And so you see the quantum number. This 1 is associated with the I square of the state. I square for the state has a value 2 because I is 1. So I into I plus 1 is 1 into 2. This 1 is the quantum. The 3 values of Iz operator, eigenvalues 1, 0, and minus 1, are the 3 other numbers that you see. So this is the lowest energy state, this is the intermediate energy state, and this is the highest energy state. So your spin 1, the magnetic field, has 3 energy levels. A minus higher energy, M is minus 1 here, this is the energy state. And M is equal to plus 1, this is the lower energy state. And you have a zero energy state because Iz is 0. So you have 3 angular momentum states. All of them have the magnitude of square root 2. I square is 2, therefore the magnitude I is square. So you can see that cos theta is either 1 by root 2 or 0 by root 2 or minus 1 by root 2. And therefore the angle theta is 45 degrees, 90 degrees, and then 135 degrees, 3 angles. So the 3 energy eigenvalues for the operators, I square, are these 3. And spin 1 nuclei, there are quite a lot of them. Deuterium, 14 nitrogen, lithium 6, these are all nuclei with the spin 1 quantum number. And spin 3 half quantum number, if you do fluorine 35, and spin 5 halves, if you do iodine 127, they have 3 half has 4 orientations in the magnetic field. The orientations have the values 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2. This 3 half is the I square associated value. So this will be 3 half into 5 halves. So 15 by the I square out. Okay. I is equal to 5 by 2. You have 6 energy levels. 5 by 2, 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2, minus 5 by 2. M is always differing by 1 between the 2 states. Therefore, this nucleus, fluorine 35 nucleus, has 4 energy levels in the magnetic field. Iodine nucleus has 6 energy levels in the magnetic field. You see that? And any nucleus with a spin quantum number I has 2I plus 1. See 4. 2I plus 1 is 2 into 3 by 2 plus 1, which is 4. 2I plus 1 here is 2 into 5 by 2 plus 1, which is 6. So for any I, 2I plus 1 levels are there. Right? Okay, now having done this part, we stop here. And so far, have you seen all these things before? I just wanted to know. No? So first time you are seeing it. So Professor Sagaraman did not deal with any of this, right? He went straight to the experiments and also the results, as I understand. Is that correct? He talked more about that. He didn't talk about the theory, right? But what I have told you is absolutely basic introduction to the mathematics of NMR. If you want to do a full course on the theoretical details of NMR, you need at least 2 semesters, 45 plus 45, 90 lectures, 90 hours of study. And if you want to be an NMR expert, you need to study for 3-4 years. By the way, I did my PhD here in Canada with one of the NMR theoreticians. Probably in those days, he was known as the best theoretician in the world. And it was very difficult to study with him. But he was a nice man and he was very friendly. And he's still in Montreal. I studied in Montreal. I did my PhD in a university there called the McGill University in Montreal. And NMR was my research team, theoretical NMR. So I spent about 5.5 years. And later, 2 of my students, PhD students, also spent 5.5 years with me to study NMR problems. So theoretical NMR, you take a long time to understand. But what I have told you is the ABC of NMR. Okay? It's not even the words, definitely not sentences, and definitely not essays, and not AI editable essays. No, that gets very, very high. Okay? So I only introduced you to the alphabets of NMR. Okay? Now, I'll go for another 10 minutes and then we have a break. I believe 9. We started at 9:30. This is what? This is 10 o'clock now for you? Maybe about 5 minutes, then I'll give you a break. Okay? And then we can come back. Just 5 more minutes. Okay. Am I sharing the screen? Now I share. So now you can see the screen? Yes, okay. So we'll do something. Okay. The theory of angular momentum, spin angular momentum operator I in Cartesian coordinates has 3 components, x, ix, iy. The z-axis is already the field axis, you remember, magnetic field. So then perpendicular to the magnetic field axis are the x and y components. Square of the angular momentum operator is a vector, a dot product of 2 vectors, I dot I, which you know if this is ix, iy, iz, this is ix, iy, iz. The scalar product gives you ix square plus iy square plus iz square. So what one does in NMR is that I square, the eigenvalues are known, I into I plus 1. Iz, the eigenvalues are known from I to minus I. Steps on. So if it is 1/2, it is 1/2 and minus 1/2. If it is 1, it is 1, 0, minus 1. I to minus I. But now you don't know what is ix and y. So the idea is to define an operator called I plus, which is ix plus iy, or I minus. This is 2 operators. I minus, which is ix, minus iy. So in quantum mechanics, all experimentally measurable quantities must be given by Hermitian operators. Ix is a Hermitian operator. Iy is a Hermitian, but I plus and I minus are not Hermitian. So if you take ix plus iiy as I plus and ix minus iiy as I minus, if you add the 2, you'll get 2ix. So I plus I gives you 2ix. If you subtract the 2, you will get I plus minus I minus gives you 2iy by minus I. Ix and iy. Why do we need this plus and minus? The plus operator is called a raising operator. The minus operator is called a lowering operator. We'll see that in a minute. What the plus operator does is the plus operator acts on the angular momentum states I but then it gives the angular momentum state I m plus 1. So if you start with half and a minus a half here, half minus a half, I plus will change it to half, minus a half plus 1, which will be half and half. So I plus on beta gives you alpha and some number. This is the coefficient that gets out. And I minus on IM gives you I m minus 1. So it's called a lowering. So you can see that I square on alpha gives you 3 by 4 alpha. I square on beta also gives you 3 by 4 beta. I into I plus 1, 3 by 4 beta. Z on alpha gives you half, and I z on beta minus half beta. I plus on alpha gives you 0. You see, it's already, this is I is half, m is half. I plus on I is half, m is half. I minus m makes it 0. Therefore, I plus on alpha cannot be raised to b. Okay. I minus, if you look at it here. I plus on beta, if you look at it. I plus raises the state half minus a half to the state half plus a half with a number which is 1. So I plus on beta gives you alpha. But I plus on alpha gives you 0. These operators are important because these are the ones which cause the resonance in the magnetic resonance. Therefore, the plus and minus operators are what is called the interaction quantities. They interact with the magnetic field to raise the spin from alpha to beta, or to lower the spin to alpha. Remember, beta is a higher energy state. Alpha is a lower energy state in the magnetic field. Okay. And states of beta are also orthonormal. Therefore, you can see that the ket alpha times the ket alpha times the bra alpha, this one. This is 1, and the bra times the beta alpha. And beta is also 1, and they are orthogonal. Therefore, you can see alpha beta product is 0, and beta alpha product is 0. Therefore, the operator I plus has a representation in the form of a matrix given like this: alpha, 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 beta, beta, alpha, beta, beta. Now, I plus on alpha is 0, so that's a 0. I plus on beta gives you alpha, therefore it's alpha, alpha, which is 1. Okay? I plus on alpha is 0. I plus on beta gives you alpha. But beta alpha is 0. So this is the representation for the I plus operator. You can immediately show that the I minus operator is a transpose Hermitian adjoint. 0, 0, 0. And the IX operator is the sum of the two divided by 1 by divided by I plus plus I minus by 2. So you sum these two matrices and divide by 2, so you get 1 by 2, 0, 1, 1, 0. And this is written as 1 by 2 times. Famous operator called the Pauli spin the half matrix for the X component of the spin. Okay. So let me stop here, and we'll continue up to about 5 minutes or 6 minutes for another hour, and continue with this algebra to introduce you to what is called the matrix representation of the NMR operators, and a little bit about their Schrodinger equation, how they are solved. Okay. So we'll stop here for the time being. And if you have any questions, please feel free to ask me. Okay. Okay. So otherwise, you have a break for 5 minutes. Okay. Yeah. Any questions? புரியுறதா? தலைக்கு வேலை போயிட்டா. எல்லாமே ஃபர்ஸ்ட் டைம் பார்க்கும்போது கஷ்டமா இருக்கும். அதை வச்சு 2 ப்ராப்ளம் சால்வ் பண்ணோன்னா கொஞ்சம் புரியுற மாதிரி இருக்கும். 4 ப்ராப்ளம் சால்வ் பண்ணிங்கன்னா இன்னும் கொஞ்சம் புரியுற மாதிரி இருக்கும். 10 ப்ராப்ளம் சால்வ் பண்ணிக்கலாலும் கான்ஃபிடென்ட்டாக இதுதான் ஆன்சர்னு சொல்லுங்க. ஓகே, குவாண்டம் மெக்கானிக்ஸே அப்படித்தான். குவாண்டம் மெக்கானிக்ஸை யாராலையுமே புரிஞ்சிக்க முடியாது. ஆனால் இட் ஒர்க்ஸ். It explains all the properties of the molecules. It explains everything that we see today, all the electronics. It explains everything, Sunder and the PC boards. Everything is working well. But we don't know why quantum mechanics works that way. It's like this. But if we understand it, we'll be able to make contribution to experiments, to understanding new phenomena. Okay? We'll see that when we come back.
Swayam Prabha. Digital India. Educated India.